Hello everyone, welcome to the channel. So in this video, I am going to implement linear regression with the mini batch stochastic gradient descent. So in the previous video, I actually implemented linear regression with a normal gradient descent. Before starting the coding part, let us have a look at the mathematical equations that will be used in linear regression. So like the normal linear regression, we will have a hypothesis, error, cost function, gradients and gradients update rule. The only main difference is that instead of passing the entire data set, we will only pass a batch of the data set for these equations. So for hypothesis, you can see the y hat batch equal to x batch dot w plus b. So xb is actually the input vector of the batch. So y hat b equal to predicted value for that batch. So likewise, we will calculate loss for the batch. We will also update the gradients for the batch. So hope you are clear so far. So let us have a look at the pseudocode for the algorithm. So first we need to know how many iteration are we going to do for the gradient descent. Next we have to shuffle the training data. So I will explain why we have to shuffle the training data in a bit. Next we have to split the input data set into mini batches. Then we have to iterate over the batch and then find the hypothesis, error, the gradients and the gradient update. So for each iteration, we have to do several update depending on the batches size. So in normal linear regression, for each iteration, we only do one update. But in stochastic gradient descent, for each iteration, we will do several updates. So that is the main difference between normal gradient descent and stochastic gradient descent. Here you can see the difference between gradient descent and the mini batch gradient descent. In gradient descent, we will use the entire dataset for an update. In mini batch gradient descent, we will split the input dataset into batches and get an update for each batch. So for gradient descent, we will just have one update per iteration, but in mini batch, we will have totally m by mb updates per iteration. So mb is the length of the input vector. Suppose the dataset has 1000 data points, so m will be 1000. Suppose our batch size is 64, so the total number of update per iteration will be 1000 by 64. So in gradient descent, we will pass the entire data set, so there will be no noise. So in a way, there is no regularization from the gradient descent itself. But in mini batch gradient descent, since we are sampling random batches, there will be some kind of noise in the gradient descent. So it kind of acts as a regularization and avoids overfitting. So mini batch gradient descent, you can say like it is a kind of regularization. So why do we need shuffling in stochastic gradient descent? So let's assume we don't shuffle the input data. What happens is that the gradient updates are very biased. So let's assume we have a data set with a feature vector x. So the first 500 rows of the feature vector x will have very small values. And the next 500 rows will have very large values. If you don't shuffle, the initial mini batches will only see small x values, and the gradients will also try to fit that values. So it will underestimate the true slope of the data set, and when it reaches the higher values, it tries to overcompensate. So the convergence won't be quicker, it will also be a bit chaotic. So when we shuffle, so the each batch will be the average of the entire data set. So you can say it is more like approximation of the entire data set. So when we shuffle, the convergence will be very smoother, and it will also be very quicker. So that's why you really need to do shuffling. So the another side effect of stochastic gradient descent is that it adds a implicit regularization because of the noise of the each batch. So it prevents overfitting. So next we can move on to the coding part. So now we can code linear regression with a stochastic gradient descent. So previously we have already done linear regression with a normal gradient descent. So I will just create a new class, linear regression SGD. So we can reuse some part of the code from the earlier implementation. So I will just copy paste them. So I have, like, while creating the object, we will pass the learning rate and the number of iteration. So for mini batch gradient descent, I will also add batch size as a parameter to pass. So let's say the default value is 64. Self dot batch size equal to batch size. So the number of instances and the number of features, these part will remain the same. We can also initialize weights and bias with 0 values. So next we have to do the stochastic gradient descent. Minimize stochastic gradient descent. First we have to iterate over the number of iterations. So next we have to shuffle the data. So for shuffling we can use random and permutation model from numpy. Permutation. So n instances, indices. So let us see what this does. Suppose n instances is 100, it returns 0 to 99 in a shuffled manner. So indices could be like 4 comma 98 comma 0 comma and so on. So this will be the shuffled array of 0 to 99. So next we have to create the new shuffled x and y. X indices. So y shuffled equal to y indices. So now we have shuffled the data. Next we have to iterate over the number of batches. So 5 I in range 0 n instances self dot batch size. So let us see what this loop does. So initially our I value will be 0. So and then the batch, if let's say the batch size is 64, so the next I value will be 0 plus 64. The next will be 64 plus 64, which is equal to 128. So and so on. So this is what this loop does. So we have to create the batch input vectors. X batch equal to x shuffled. We have to plug the batch of 64 from the x shuffled input data. So I to I plus self dot batch size. So in the first loop, we are essentially picking the 0 to 64th entries. In the next loop, we will be pick the data from 64th entry to 127th entry and so on. So similarly, y batch equal to, so I will just copy paste this. So y. So now we have created the x and y for the batch. So the next part will be the mathematical equations that we saw earlier. So first is the forward pass. So forward pass predicted y equal to np dot x batch self dot weights. Add a bias value to it. So error equal to predicted value minus y. So here y is y batch. So next we have to find the gradients. So dw equal to, so the formula is here. So dw equal to np dot, so x dot t. So here x is x batch. Error. So we have to divide over the number of data points in this batch. So length x batch. Similarly, for bias equal to np dot sum error, length of x batch. So now we have found the gradients for weights and bias. Next is the update rule. So you can see that there is no batch specific variable here. So we can just reuse the earlier coded part. So now we have implemented stochastic gradient descent. So we can have a review of what we have done. So first we have shuffled the data. This is very important, as I discussed earlier. Next we have to iterate over all the batches for each iteration. So you can see for each iteration we are going through entire data set in batches and updating the weights for each batch. So this is basically what is called as mini batch gradient descent. So next, the prediction value, the predict method. This is same as the normal linear regression. So now we have implemented linear regression with a stochastic gradient descent. So now we can use a toy data set and train our model, and also finally evaluate our model, and then we can compare it with the inbuilt linear regression model from scikit-learn. So I have already like copy pasted some code. This just imports a diabetes data set from the scikit-learn, and also the data is already standardized, and I also split the data into training and a test data set. You can just pause and have a look at what I have done. So we can start the training the model part. So we have to initialize the model. So linear regression SGD. So we can pass the learning rate, iteration, and the batch size. So I will just pass the iterations for now. And the batch size we can keep it as 64 or 128. Let's say 128. Next we have to fit the model. We have to pass the training data set. So X train and Y train. Next we have to predict the model. Here we have to use test data set. So we can keep the variable as Y prediction. So we can also print the predicted value. So now we can run this code. So you can see we have an output. The values are 160, 163, 157, and so on. So now I will import the scikit-learn linear regression from scikit-learn dot linear model import linear regression. So model equal to linear regression. So model dot fit X train Y train. So the prediction value, so the predicted value equal to model dot predict X test. So we can also print the predicted value. So here you can see the output is 139, 179, and so on. So I think the 1000 iteration isn't enough. That's why the model hasn't converged yet. Now we can increase the iteration to 10,000 and see what happens. Okay, now the results are much better. So the iterations is 10,000. So the output is 140, 181. Here the output is 139, 179, 134, 291. Here it is 140, 294. So even at the end 111, 85. Here it is 115 and 78. There is a huge, somewhat big deviations here, 85, 88, 81. Let us see what happens when we reduce the batch size. So still the model is more or less same. We can even change the learning rate. let us keep it as 0.5. So still the data is more or less same. Now what I will do is I will also like get a prediction from the linear regression that we coded earlier to have an idea of how the output was there. So since the name is linear regression here, also the scikit-learn linear regression model also has the same name. I will just rename it to linear regression GD. So this way there will be no naming conflicts. There is no batch size. Alpha we can keep it as 1. Okay, now I will just rerun the entire code. Okay, here you can see our SGD has actually performed better than normal gradient descent. I think the values are 172, here it is 140, here is 139, it's 84, here it is 88, here it is 78. So what happens is that the original linear regression is actually somewhat overfitting. The addition of stochastic gradient descent has actually acted as a regularization here. So this is the most like accurate prediction you can say, because this uses closed form equation. So I hope you guys understood the difference between normal gradient descent and stochastic gradient descent, and also you guys have an idea of how to code now. So I also given a comparison between all three versions. So in the next video, we ourselves will code the closed form equation and see how it stacks up to scikit-learn linear regression model. Thank you. See you in the next video.